Hey guys, so welcome back. Today I'm going to be doing this example for you, and so let's read it over. So a semicircle with a radius a in the first and second quadrants with the center of curvature at the origin has a positive charge plus q distributed uniformly around the left half of the semicircle, and a negative charge minus q is distributed uniformly around the right half of this semicircle in the following figure, which is down here. And then we're being asked for the magnitude and direction of the net electric field at the origin produced by the distribution of charge. Okay, and so just first let's talk about the quadrant system because that's how we're given the description, just in case you weren't given this diagram and you had to identify the first and second quadrants. A reminder that this is the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. And so this diagram is in the first and second quadrant because I have my axes here, as you can see in white. And so that is the quadrant system. And now let's talk a little bit about this diagram here just before we dive into the math. So here we have let's say it's a band of wire, just a length of wire in the xy. I'll label this as the x and this is the y plane. And then let's say that this is positively charged and this is a negatively charged part of it. And so because this is positively charged, if you remember, the positive charges give away electric fields, and then the negative charges take them in. And the way that I like to remember that is that I say it goes into positive, out of negative, and into positive, and out of negative. And so, into positive, out of negative, into positive, out of negative. And so that is how I like to remember. It's just a little saying I have. And so if we were to draw that on here, we could see that this, let's say this point on the positive side of this semicircle, it would be contributing an electric field here, and then maybe this guy would be going over here, and then these guys would also all be kind of bending towards here. There would be some overlap, but remember, electric fields can't intersect. And so what I mean when I say overlap is just that the general flow of the electric field is going to be from this positive side to this negative side. And so whether that is going like I've drawn it here, or whether like this, you can't really say from the diagram, but that is, this is the general flow of the electric field. And so I'll just label that here. I'll say the net flow of the electric field. Field. There we go. And I'll just make that field a bit clearer. Okay, and so that net flow of the electric field is headed in this direction, and keep that in mind when we're solving the problems, and this has a radius a here. And so because we're being asked for the magnitude and direction, we now have to solve for the magnitude produced at the origin, and the origin is just this guy here. I'll call it point B also, just because we already have an A, so I don't want to confuse those two. And so we're looking for the net electric field at this point B produced by this charge and this absence of charge over here, this negative charge. And so thinking about that, let's just go with what we established in the video where I talked about general integrating electric fields, and that was that the electric field is equal to k, the integral dq over r squared with the unit vector r hat, right? And so if we have this electric field here, then we can start with our diagram and say, okay, well, how do we apply it to this equation that we have? Because we know that in these types of scenarios where we don't just have a formula we can plug and play with, we're going to need to integrate to derive one on our own. And so looking at this, because it's a band of wire, whenever you're dealing with a band or a line of wire, you're usually going to be dealing with linear charge density. And so linear charge density is charge over lambda, this is lambda, equals charge over, I'll just put L. This is how I draw my L's, this little loop. And so for charge is equal to Q over L, I'm just going to draw here a dq and a dl to show that I've broken up this, this length of wire and this other length of wire into dq's and dl's. That's just how I draw it on the diagram. And so this lambda is equal to charge over L, and this is going to be a constant because we said that the distribution is uniform on both sides for both the positive and the negative. So this Q is staying the same and this length is staying the same, so this guy is going to stay the same. And so if we want this dq, we don't have a dq here, but if we can make one by just saying, okay, dq dl, by taking the derivative with respect to L, will give us this equation, and that makes sense, right? Because these d's will just cancel. If you've taken calculus, you will know that. And so this is how we can think of our dq, and then if we isolate for our dq, because we want to be able to sub in, we can just then write lambda dl equals dq. Okay, and so that's our equation there, and then we can sub that in to here now. So I'll just write that out again. Equals k, the integral, and then I'll switch back to this teal color, lambda dl, and then I'll switch back to purple. And I'll just leave this as the unit vector r. And then I also want to talk about this r here, and because this is the distance from the point that we are trying to find the electric field about, right? And so because we are trying to find the electric field about this point B from any point dq, which will be along this wire. So dq, I'll just draw it over here, it could be over here or it could be up here, right? So keep that in mind when you're thinking about these types of problems. And so because of that, because of it being anywhere, we can say that the radius is going to be our r, because the distance from here is the same as the distance from here is the same as the distance to any point along this wire. So that's going to be a squared. And then this is our equation that we have now, and it probably would also be a good idea to throw in some bounds here, so I'll do that now. And so looking at this shape, we usually like to set our bounds with whatever dx or dl we've chosen here, with whatever length of measurement we've chosen. But in this situation, when you think about it, what are we truly going to be integrating along? Because if we integrate just along, for instance, the x, then we're going to only get this component, as in the x plane, in a physics sense. We're not going to take into account this curvature, I guess you could say. And that applies for the y-plane as well. If we were to integrate in the y-plane, you know, we're just going to take into account this plane and not the actual curvature of the object. And so thinking about that, we need something that's going to take into account the geometry of this object. And so I encourage you to think about, if you know any way to do that, or if you can think of something that would do that, just pause the video and think. Okay, and so I know that can seem like a very broad question the way I posed it, and so it's okay if you didn't get it. But the way that I approached this problem, at least, after attempting and failing multiple times, was to use angles. And so I used theta equals s over r to help me solve this. And this, if you weren't introduced to it sometime in your education, is a really important formula where this is an angle measured in radians, so I'll just write rads. This is the arc length, so that is like the angle subtended by this, or not the angle subtended, but the length subtended by this angle. And this is the radius of the arm that sticks out. So if we were just looking at it in this terms, you know, we would have this be our theta, this would be this length here, be our s, and this a would be our r. Okay, and so I'm just going to undo that so our diagram's still clean, and I'll write radius there. Okay, and so thinking about that, we can now have an expression for this arc length here that takes into account the geometry of this shape. And so thinking about that, what's going to change as we move along this arc? If we were, because what we're doing here is we're trying to say, okay, take each dq and add it up. Remember from my intro video where I talked about the basics of integrating an electric field or electric potential, which I would recommend watching if you haven't watched. It'll give you a lot more context behind this and allow you to solve these problems on your own. These dq's that we're adding up are all going to be measured at an angle theta to here, or they could be measured. They don't have to be, but they could be. And so because of that, our theta is going to be changing as the arc length changes. So I can denote that by just putting a d, standing for delta, standing for change, right? D equals delta, which equals change. Even though we usually don't write this part, I'm just writing it for your understanding. And so now that we have this, we can exchange this for L, because our S is really just L, because I just denoted it as L for the length, for the infinitesimal length here, but S is the arc length and L is also the arc length. So these are interchangeable, this S and L. So if I wanted to isolate for my ds or my dl, I'll write that just a note, ds is equal to dl. And then if we wanted this dl now, I can just go r d theta equals dl, right? And so now I can sub that into this equation, and that'll help me because then that means that I can use angles as my bounds because I'll be integrating over d theta, so geometrically it will make sense. And so if I'm going to think about my bounds, I could go from 0 to pi, because I'm going to use radians, because remember this has to be in radians. That's a very important part. A lot of people trip up on that. And so I could do that, or what I could do is I could use the geometry of the problem and say, well, this is symmetric about the y-axis, so I can just write a 2 here, and then that's going to be 2 times this, because this side from 0 to pi over 2 will also give me this side. And so because it's symmetric, this makes sense. And so I can use that. And so now I'm going to go ahead and sub in that substitution I made. And you can still write it with the angles here. It's just that you won't be able to mathematically do it. This is a valid step here. It's not that this is illegal or anything mathematically. It's just that you wouldn't be able to evaluate it because this L isn't a angle, a infinitesimally small angle measurement. It's an infinitesimally small length measurement. And so if I'm writing this, and I'm just going to fit my r in there, right? And I still have my unit vector. Okay, and so now I think it's a good time to talk about my unit vector here. And oh, sorry, I should also note that this r is actually just my a, so I can write this as a. I'm going to make that cleaner for you actually, sorry guys. So this lambda is a because r is equal to a in this situation because it's simply the radius, and so I can write lambda r is equal to a, lambda a, and then d theta over a squared, and then I can just cancel that a, and I'll just have the a on the bottom, and then I'm still going to have my unit vector. And so that's what I want to talk about next is the unit vector. And so here you could think about the definition of the unit vector for this, which is, you know, r hat equals r over the magnitude of the vector r. But in this situation, I think it's easier personally just to think about, okay, so I know that the net field is flowing in this direction, right? And so thinking about that, I need to somehow express that in my equation, right? And so if I'm going to express that in my equation, because the contribution of each electric field coming from a different dq along this ring is going to be coming at a different angle towards this origin. And so if I just sketch that out on this diagram to give you a bit better sense of what I mean by that. So here, for instance, if I have, let's use yellow. So if I have a yellow electric field, I'm just joking there. The electric fields don't actually have color, of course. And so if I have a yellow electric field, and let's say, you know, it's flowing something like that. Like, I don't know where it's actually flowing, but let's just assume it's flowing something like that, right? From the positive to the negative. And so it has this theta and this theta. And so because I know that the flow of the electric field is going to be in this direction and it's going to be along the x-axis, I know that I can use cos theta because I just want to project this electric field onto the x-axis to find out its contribution to the origin here. And so that's how I like to think of it. And so if I'm going to write out this next step, and I'm also in this next step going to take this lambda out because as I discussed earlier, lambda is a constant. So lambda k integral 0 pi over 2 and then d theta. And I can also take this a out because a is a constant. And then, like I said, this unit vector, r hat, is going to be equal to cos theta. And then I'll just write from geometry. And so I'm just going to move this guy over actually to make room for my cos. So that is cos theta, right? Okay, and so in this situation, now I just need to integrate it. And the integral of cos is sine. And just in case I'm not sure, I have a little way I like to remember this. So I remember that the derivative with respect to x of cos x, rather, of cos x is negative sine x. And I remember that because to go towards sin in most religions is a bad thing. And so when you're integrating, when you take the integral of cos x, you're going towards sin again, but because integration, everything is backwards, it's actually going to be a positive sign because it's good to go towards sin now in this reversed direction. Anyways, that's just a little side note. You don't need to remember it that way or anything. I just find that sometimes these little memory tricks can be helpful even for something that I use so often as that. And so even in that case, so we know that the integral of this, so we have lambda k over a, the integral 0 pi over 2. Actually, I'll just do the integration all in one step. And so this will be sine x, and then evaluated, well, I can leave it as sine theta, I guess. So I'll leave that as sine theta, sorry guys. From pi over 2 to 0. And so if I'm evaluating that, I can just simply write this sine pi over 2 minus sine 0 with the brackets. And so when evaluating this, sine of pi over 2, if we think about that on our unit circle, is going to be up here, and that guy is going to be 1. And then if I do sine of 0, that guy is going to be over here, and that guy is going to be 0. So I can just write this as 0. And so what I'm going to end up getting is this is all equal to pi k over a. And I just realized that I forgot the 2 throughout this whole process. So that's my fault, guys. Sorry. So I'm just going to write this 2 in. And this is a good answer. You know, it's a good answer, but because in some of my other videos I talk about this too, because the question asked us about a charge q, it's polite to give the question back and answer in the same variables is how I like to think about it. And so in that situation, we're going to need to have a q in here. And so you may say, well, how are we going to do that? And like as you do more of these problems, you'll see that you can look back at your previous work and usually there'll be some type of simplification you can make, or sometimes it won't simplify it actually, but it will get the variable that you want in there. And so if you look back at this work, we will try and find something that we can sub in for q. And indeed, we have this relationship here coming back at us again. And so what you'll notice here, though, is that we don't have a k or an a in this equation here. And so we need to either figure out how to get this a out of there or get an a into here. And so we can't really put get an L into here, and we can't really get an L into here that easily. And so the way that I did this was I did lambda, because lambda is still equal to q over a, or q over L, sorry, q over L, and this length is the length of the segment, right? And so in this situation, it's going to be half of the circumference, and we know that half the circumference of a circle is a half pi r squared, or just r, sorry, but because our radius is a, we can just write that as a. And so we know that this is our lambda, and so if we rearrange for lambda in terms of this, I'm just going to simplify it actually. We can write 2q over pi a is our lambda. And so if I go to sub that in now over there, which I can do 2 and then q k over pi a squared. And then this is going to be equal to our electric field. And so one thing to keep in mind here is that because, oh, sorry, actually, this should not be 2 because it's going to be 2 times 2. And so that's going to be 4. I forgot to add that. And the thing, as I just demonstrated perfectly, is that mistakes happen all the times in these type of questions. And one thing that I would really recommend doing is at each step, think about the answer that you're getting and say, does that make sense? And that's how I caught this answer here, because I thought, well, 4, I thought it would be more than 4 because I doubled it, and then wasn't there like a half hanging around there, and so I have that in the back of my brain, and that's why this didn't really compute for me. And so I would really recommend like every step of the process. It does take more energy, but you'll catch more errors that way, and I would recommend practicing the homework that way because you will also then demonstrate that in your exams. And so that is our answer for this question, and that's really all I had for today. So I hope this helped you guys understand this example, and have a good one. So yeah.